In 2009, astronomers were watching a star 25 times heavier than the sun suddenly flare up, brightening to over 1 million times the sun's luminosity. They expected a supernova within weeks. Instead, over the next few years, the star simply faded into nothing, and when they checked years later, it was gone with no explosion ever recorded. This was not science fiction. It happened in a real galaxy 22 million light years away to a star cataloged as N6946BH1, and it forced astronomers to ask an uncomfortable question. What if some of the most massive stars in the universe do not die in the explosion we always picture and instead just switch off? For most of the 20th century, the story of a massive star's death was simple and dramatic. A star burns through hydrogen, then helium, then heavier elements, building up layers like an onion until its core turns to iron. Iron cannot be fused for energy, so the core suddenly loses its support, and in under a second, it collapses from the size of the Earth down to the size of a city. That collapse should trigger a supernova, a blast that outshines an entire galaxy for weeks and seeds the universe with the elements everything is made of. But here's the part most people never hear. When physicists actually try to simulate that explosion on a computer, in the vast majority of cases, it fails. The core collapses and slams to a stop at nuclear density, sending a shockwave rushing outward. But that shock has to plow through the still, infalling outer layers of the star, and it loses energy doing it, ripping iron nuclei apart atom by atom. Within milliseconds, the shock stalls out, sitting still about 100 to 200 kilometers from the center. No longer an explosion, just a standing wall of gas. For decades, this was the central embarrassment of supernova theory. The explosion that forges gold and seeds planets with iron kept refusing to happen in the simulations. The fix, worked out by Hans Bethe and collaborators, was that neutrinos streaming out of the newborn dense core can slam back into the stalled shock and reheat it, and turbulence behind the shock helps push it the rest of the way. But that revival is not guaranteed. It depends on a delicate balance on how much mass keeps raining onto the core, on the star's internal structure, on pure luck in the turbulence. And when that balance tips the wrong way, there is no plan B. The shock never revives, the material never gets ejected, and the entire star, without any explosion at all, just keeps falling inward. That silent failure has a name. Astronomers call it a failed supernova, or more bluntly, a massive fail. The star's core keeps swallowing infalling matter until it crosses the threshold for a black hole, and the outer envelope, instead of being blown away, gets swallowed right along with it. This was a theoretical prediction going back decades, but nobody had caught one in the act, because how do you observe an explosion that never happens? In 2008, astrophysicist Christopher Kochenek proposed a strange kind of survey. Instead of watching for new stars appearing as supernovae, watch nearby galaxies for stars that quietly disappear. His team used the large Binocular telescope in Arizona to monitor 27 galaxies within about 10 million parsecs, repeatedly imaging them for years, hunting for exactly one thing, a star that had been there and then simply was not. In 2009, they found their candidate, a red supergiant called N6946BH1, 25 times the mass of the Sun. The star brightened suspiciously in 2009, exactly the kind of pre-explosion flare theory predicted. Then, over the following years, it dimmed and dimmed and dimmed. By 2015, Hubble could not see it at all in visible light. It had gone from ordinary star to completely invisible. This is where the story gets genuinely detective-like, because vanishing is not proof of death. The star could have just wrapped itself in a shroud of dust and be hiding, not dead. So the team checked infrared light, since dust glows in infrared even when it blocks visible light. And if the star were still alive and just dust-covered, it should blaze in the infrared. What they found instead was a faint fading infrared glow, far too weak to be a hidden but living star, and consistent instead with debris slowly spiraling down onto a newly formed black hole. Follow-up studies, and even a look with the James Webb Space Telescope years later, still found no bright surviving star at that location, only a faint smear. So why does this matter beyond one weird star? Because astronomers had already noticed a strange gap in their supernova records, nicknamed the red supergiant problem. Stars up to about 17 or 18 solar masses show up plainly as supernova progenitors in pre-explosion images. but red supergiants between about 20 and 30 solar masses, which definitely exist in large numbers, almost never show up as supernovae. For years, nobody knew if those heavier stars were exploding in some way astronomers were missing, or if they were skipping the explosion entirely. A failed supernova, a star collapsing directly into a black hole, would explain the gap perfectly. Those stars are still there, they are just dying invisibly, which is exactly the mass range N6946BH1 falls into. Based on that survey, the team estimated that as many as 10 to 30% of all massive star deaths might end this way, silently, without ever producing the fireworks we associate with a star's death. That is a staggering fraction, considering supernova are supposed to be one of the most reliable, most visible events in the universe. For years, N6946BH1 stood almost alone as evidence. A strong case, but a single data point, and skeptics pointed out you cannot build a new category of stellar death on one ambiguous star. Some researchers even suggested it might still be alive, wrapped in an unusually thick eruption of dust, similar to the famous outbursts of the star Eta Carinae. Then just recently, astronomers found a second, even more convincing case, and this time in our closest large neighbor galaxy, Andromeda. Astronomer Keishale Day and his team were combing through years of archived infrared data from NASA's NEOWISE space telescope, hunting for anything that brightened and then vanished. Buried in that data since 2014 was a star called M312014 DS1, originally about 13 times the mass of the Sun, but stripped down to roughly 5 solar masses by ferocious stellar winds. It glowed brighter and brighter in infrared for about 3 years, then faded dramatically, leaving nothing behind but a shell of dust and a whisper of leftover light. Crucially, this star's collapse matched a prediction made back in the 1970s, decades before anyone had the technology to test it. That direct collapse into a black hole should leave behind exactly this kind of signature: a faint infrared afterglow from a slow, sudden puff of gas. The dying star sheds in its final hours, not the blinding flash of a supernova. According to the team's modeling, the star's dense core likely collapsed into a black hole in a matter of hours, and what we still see today is not the star, and not even the black hole directly, but leftover gas and dust swirling around it too fast to fall straight in, forming a disk that will keep feeding the black hole for decades, like water spiraling slowly around a drain before it finally disappears. One researcher on the team called this discovery the most surprising of their career, and for good reason. The evidence had been sitting in public data for over a decade before anyone noticed a star had quietly died in it. That itself says something unsettling, that the universe may be full of these silent deaths, hiding in plain sight in archives nobody has finished searching. If direct collapse really happens to a meaningful fraction of massive stars, it reshapes several things at once. It helps explain the strange masses of black holes detected through gravitational waves by observatories like LIGO, some of which are heavier than models of ordinary supernova remnants can easily explain. It also means the universe may be forging slightly less gold, iron, and other heavy elements than assumed, since supernova are one of the main furnaces that scatter those elements into space. Astronomers are not finished hunting. Upcoming surveys, especially the Vera Rubin Observatory's decade-long scan of the entire visible sky, are expected to repeatedly image billions of stars, giving researchers their best chance yet to catch more of these silent deaths as they happen, not years later in an old data archive. So the next time you look up, remember that some of the biggest, brightest stars up there might not end in the blaze of glory we expect. They might just quietly fade out one day, leaving nothing but a black hole and a faint whisper of dust, and we may only notice decades later when someone finally checks the right old photograph. If you want to keep chasing stories like this, the ones hiding in plain sight in the universe's data, subscribe, because there are more vanishing stars out there waiting to be found.